Welcome back, everybody. AP Chemistry, Unit 7, Section 2, taking a look at the values of Q now as an equilibrium quotient. Okay, I'm going to start by actually reviewing a couple of things with us in terms of what we did in the last section. And this is kind of weird to be kind of reiterating what I just did, but remember that the equilibrium expressions involving concentrations or pressures only involve substances that change from the initial to equilibrium conditions. And this only applies really to those things that are aqueous or gas in nature, okay? Pure substances like a liquid or a solid really don't do anything for concentrations. They just change the amount of things as we go. Okay, so let's take a look at what I mean by this if we were going to take a look at equilibrium expressions or my K values of something in the following reactions. Notice if I'm looking for my equilibrium constant, my K value, notice that this acts as 1 because it's a solid. This acts as 1 as a solid, and here is my gas. So really my equilibrium expression is just going to be a value of my carbon dioxide to the first power. In this particular one, I see that my K value is a solid and a liquid in this case, and it's really my expression is only a value of my chlorine as a gas, and again, I only have one of those. Lastly, I have my expression is going to be a function of, well, here's a solid, and here's water. But be careful, it tells me that this water is in the gaseous phase. So it is indeed going to be water, even though we would typically think of it as a liquid. And notice that it would be raised to the fifth power because of that. So what I'm doing in this is showing you that the values of solids or liquids effectively just are a multiplier of 1 if we find those constants. All right. So what we're doing with equilibrium constants is we're predicting several things. How far the reaction is going to go in terms of products or reactants. If I have a large K value or a small K value, that's mostly reactants or mostly products. But one thing that we do want to take a look at is if I'm looking at a K value, what does that really mean in terms of which direction? If it's mostly products, I know it's going to the right, and not as much of a K value, it's mostly to the left. But we can also take a look and figure out that direction by using my reaction quotient, okay? If we're not in there, we would take a look and calculate our Q value to tell us which direction it's going to be going. So notice that if the Q is equal to the K, it's done reacting. It's already in equilibrium when we're there. But if we're looking at changes of things, if I have my Q value ends up being larger than my equilibrium value, that means that everything is going to be going in direction of the reactants. In other words, I'm going to lose products, and I know which direction that change is going to be going. If I have a small Q value, I know the reaction is going towards the right, and it's going to be moving in the direction of those products. Okay? So, given that type of scenario, I can look at my K value, but really let's take a look at it's a function of the concentrations, isn't it? And so we'll be able to figure out and what's going on if the reaction is done. If the reaction is going to be transitioning, which direction will this reaction be going, okay? In each of the three trials. So let's solve for Q in each of these. Now Q is going to be a function of my I should write the equation up here, is going to be a function of my ammonia. And notice that's to the second power. And it's going to be my nitrogen to the first power times my hydrogen to the third power. Okay, that's H2 there. Okay, so let's plug in our values. We see that I have 0.001, and that's going to be squared over my 0.00001 times my 0.002, and that's to the third power. So in this case, in this first trial, I have 0.000001. Okay, so there's 5 zeros there. 0.00001 and 8 times 10 to the negative 9. Okay, that's 0.002 cubed. And so I get a Q value of 1.3 times 10 to the 7th power. Okay, that's a positive 7 power. Now, what does that mean? That means that it is much larger than my K value. So I know that this direction, this reaction, I should say, is going to proceed to the right. I've got a lot more reactants than I do products, so I know that this reaction is going to go toward the products. Or, I'm sorry, I'm looking at the wrong line. That's going to be going to the left. My Q value is larger than my K, and so my reaction is going to be going to the left, okay? I've got way more product, that's what I should have been saying, than I do with my reactants, and so it's moving in that direction. Let's take a look at trial number 2 now. My Q value is going to be the 0.0002 now squared over the 0.000015 to the first times my 0.354, and that's going to be to the third power. That ends up being 4.0 times 10 to the negative 8 over 6.7 times 10 to the negative 7. If I divide that out, I end up with an answer of 0.06. Now, my Q value equals my K value, doesn't it? This reaction is done, so I know this is my final strength of all my reactants and all my products. That's what my Q value is telling me. Now, lastly, we're going to be taking a look at this one, and I see that I end up with a 0.0001 squared over 5 to the first times 0.01 to the third power. That ends up being 1 times 10 to the 8th, negative 8 I should say, over 5 times 10 to the negative 6. My Q value ends up being 0.002. Now, that is definitely less than my K. So the reaction is going to be going to the right. I'm going to be making more and more of these products as we go in that direction. So this is what we use my Q value for, is to figure out which direction could this go in each of those trials given different solutions. Now, if we take a look at an equation like, or a question like this one, I'd have to find my Q value for a couple of things. Because as I look at this equation, I'm seeing I've got hydrogen and fluorine gases is going to be making hydrofluoric acid. These are all gas phases, okay? We want to watch out because it says of all the species of each reactant and product, 3 moles of everything in a 1.5 liter container. So be careful. We have to divide everything by 1.5 because molarity is moles over liters, isn't it? So I want to know how much I have of each reactant and each product. That gives me 2 molar concentration for everything, okay? So if I look at hydrogen and fluorine and hydrofluoric, I start at the beginning of all of this with 2 molar. Now, I want to know at the end of all of this reaction, I want to know what do I end up with. But the problem is I don't know which direction this reaction is going. I see my Kc value is this. I would assume that it's, we get a lot of products out of there, but we don't really know at this point until I pit my K value against my Q value. So let's figure out which direction this reaction is going to go first. Okay, that's what we're solving for. So Q is going to equal my 2 squared. Okay, that's my hydrofluoric. That's going to be over my 2 of my hydrogen times my 2 of my fluorine. Okay, notice that ends up being 2 squared over 2 squared. And so I end up with a value of 1. So Q ends up being less than K. So if Q is less than K, it means this is going to favor the products. It means that my reaction is going this direction. So I'm going to lose a certain amount of reactant, aren't I? I just don't know how much. I have 1 hydrogen, I have 1 fluorine, and I have 2 of my hydrofluorics. So this is going to gain 2x. Remember, I knew which direction this is going. That's why I knew to put a negative in front of each of these. So at equilibrium, I end up with a 2 minus x, a 2 minus x, and a 2 plus a 2x, don't I? Okay? Now, here's the problem. My K value is quite large. I can't just simply cross out my x's. Okay, so we just got to keep on going and see what we end up with. My Kc is 115. That's going to equal 2 plus 2x squared over 2 minus x times 2 minus x. What is that? Well, 2 minus x minus 2 minus x is 2 minus x squared, isn't it? So I can do something kind of tricky here. You guys are going to like this. I can't just cross out my x because k is too large. I've got to take it into account. However, notice both of these are squared. So what if I just took the square root of everything? Ooh, that's pretty clever. So let's take a look and see what this ends up being math-wise. If I took the square root, I end up with a 10.7 equals 2 plus 2x over 2 minus x. That essentially just got rid of those squareds. Okay, now let's multiply both sides to get this all even. Let's multiply both sides by 2 minus x. Okay, if I do that, I end up with 21.4 minus a 10.7x. That will equal my 2 plus 2x. Now let's combine the like terms. Notice this is just algebra, guys. This isn't too bad. If I combine like terms, I end up with 19.4 equals 12.7x. So I got my x's to the same side. I brought this guy over here, and if I bring this guy over here, remember I subtract by 2, so that's how I got 19.4 minus 12x. Therefore, my x, divide both sides by 12.7, my x ends up being 1.53. Okay, so let's go back to the scenario here. I have 2 minus x, 2 minus 1.53. Okay, 2 minus 1.53, that ends up being a 0.47. Okay, 2 minus 1.53 gives me a 0.47. And then 2 plus 2x. Well, 2 times the 1.53, add 2 to that, I end up with 5.06 molar. Okay, and that's in my hydrofluoric. So these are pretty cool. You just kind of slow down. You got to figure out which direction is it going first, and that way, if we found that Q is going to be greater than X, or Q is greater than K, then I would just subtract this, wouldn't I? So you just know which direction, and when we are doing this step, we're just solving for which direction that change is going, and we do exactly the same stuff that we did in the first set of problems from section 1. Guess what, guys? That's it. This is a quick video, and now we should be able to do all of these things, and we'll be doing some labs with them. So good luck to you, and I think you'll find this is pretty